Okay, so we're very happy to have Adar, another one of our new postdocs, not visiting, but now here from Stony Brook. And he's going to tell us about some recent work on the large charge expansion.
Thanks. Yeah, so I'm going to start by just reviewing the large charge expansion in general. It's going to be some informal or very general thing, and then a bit more technical about my work about applying this large charge expansion, specifically to the CFT bootstrap program, and specifically to theories with moduli spaces. Okay, so let's talk about what the large charge expansion tries to do. So there's a problem, which is physics hard. I'm sure you've all encountered this problem, and physicists have one solution to this problem, and that is perturbation theory. So almost everything we know how to do is to solve the free theory very, very well, and then take small informations away and order by order in some small coupling to solve these theories. So famous example is QED, which has defined structure constant, which is very small, and then you can do perturbation theory, get very good results that are very close to actual nature. Of course, once you're done doing this over and over and over, you want to do things that cannot be solved with perturbation theory. And an example of something we cannot solve with perturbation theory is QCD, which has a coupling, which in the IR is very, very large. And this is away from any perturbation. So to still keep proceeding, what people do is they try to do perturbation theory even harder. What you do is you look for small parameters that don't actually exist, but are some more generalized sense of a small parameter. So you become more creative. And you just introduce small parameters out of thin air. So my favorite example is the epsilon expansion, where you work in non-integer dimensions, you work in dimensions that are 4 minus epsilon, then expand for very small epsilon. And this allows you, for example, to start the Ising model, which is inherently strongly coupled. There's no small parameter, but still this epsilon gives you some nice small parameter. Another example is the large N expansion, where you expand in a large number of degrees of freedom. And one more example of what I'm going to talk about today is the large charge expansion, specifically in the context of conformal field theories, where if I look at any conformal field theory with some symmetry, and I focus on a specific sector of operators with very large charge, you can do an expansion of some observables in an expansion 1 over Q, where Q is your charge. So even in inherently strongly coupled theories, you still have some weak coupled parameters that you can try to do computations in. Okay, so let me talk about what the philosophy is of this large charge expansion. The idea is to write down effective field theories for Goldstone bosons. So let's see how this happens. So first, let's just take some random theory and try to take large charge limits and see what happens. So I'm just going to take in d equals 4, a complex field phi, and write down Lagrangian. Some attracting theory. And now I want to take a sector of large charge. One way to do this is to add a chemical potential. In some sense, if I take large chemical potential, that's basically the same as taking large charge. It's fixing a large background charge for that system. The way you do this is you take your Lagrangian, you just replace the time derivative with dt minus I mu. If you take this and plug it back in, what you're going to get is this same kinetic term, some mixed term, mu phi or dt phi. And then importantly, the mass term changes. So our chemical potential shows up as a negative mass term. And at large enough chemical potential, what happens is that now we have an instability, and now we're going to see Higgsing. So large enough mu, the mass is negative. So if mu is very, very large, we see a Higgs mechanism. And as a result, we're going to see a Goldstone boson, non-Goldstone boson.
No gauge field.
No gauge. Yeah, I'm sorry. Higgs is not the correct word. We have spontaneous symmetry breaking. And this is a general phenomenon that happens at large charge, at large chemical potential. At large chemical potential, we expect our symmetry to be broken to get a Goldstone boson for that corresponding symmetry. This is the case in QCD at large baryon number and in many other examples. So now I'm going to take this for granted and try to see what mileage I can get out of this statement. So let's take one step further and now assume that I have a conformal field theory instead of just a random QFT and add large chemical potential. So what I'm going to do is write down an effective field theory that describes this configuration. So what we expect to see is that our massive degrees of freedom in the simplest case are just this single Goldstone boson. It's called chi, which is a Goldstone boson. Now I'm going to write an effective field theory. The EFT, the way you do this is you do an expansion derivatives, and the only constraints you have are your symmetries. So we have one symmetry, which is just the symmetry that this came from. Chi has some translation symmetry, which is the U1 that was spontaneously broken. But we also have Weyl symmetry or formal symmetry that was spontaneously broken. And now we use these two symmetries to write down all of the possible terms that are compatible with the symmetries. And in order by order derivatives, we're going to get some EFT. So what's the leading term that we can write down for this field theory? Chi has dimension 0, just giving dimension 0. So d chi has dimension 1. So the leading term we can write down is d chi to the power 3 over 2.
We're in 3D.
I'm sorry, yes, I'm 3D. Yeah, let's do 3D for now. And general dimension, I just have d here. So this statement is now true for any CFT as long as I have a U1 symmetry. I expect that a large chemical potential, it's described by this very simple effective field theory.
Can I just ask, like, is the assumption of spontaneous symmetry breaking because you can, like, that's the only case where you can get mileage out of this form?
No, this is
That is-
very general. Yes, there's some symmetry arguments in general. I mean, okay, basically what I'm doing is setting some background charge.
Right.
So my ground state is charged under my symmetry, and so the symmetry is spontaneously broken.
That's absolutely not true.
It's not. What do you mean in general? I mean, in a generic CFT, this is what you expect. I
don't know, that's a measure problem. I don't want to just compare measures, but there's lots of examples where it's not true.
like
The dumbest example is a free Fermi gap. But there's lots of interesting models where something more interesting happens. Sometimes you get symmetry breaking, but not just that.
even the free Fermi gas, if
Free Fermi.
large enough chemical potential, and the free Fermi gas. Yes, that's the only example you can give me, right?
There are also Fermi gases that are sufficiently repulsive interactions.
But then they go back to the free Fermi gas, right? Okay, so it's a free. I agree. The free Fermi gas is the only example
That's
I'm
a
aware
prime
of.
example. There are richer examples. For example, there's examples where there is symmetry breaking, but there's many more bulk.
Yes, I agree, but no, but this is still true. I agree, and we're going to talk about those examples. But yes, except for the free Fermi gas, you always expect at least a Goldstone boson for the symmetry plus whatever other degrees of freedom that might be there. In supersymmetric theories, you're going to get some other module.
I'm just saying, now there's lots of examples, and now it's like huge to do this.
No, there's only one counterexample. You've only given me one so far.
You have a different measure though.
No, one is small, whatever measure you're using.
But what, there's no theorem?
I agree,
And,
yes,
tomorrow you might find an interesting example, it's not
Yeah.
true.
that's true, yes. Except for the Fermi gas, all known examples obey this. Yes, I think this statement is true.
Scott, who's added the chemical potential, how do you see the Lorentz?
How do I see?
The Lorentz.
Yeah, I'm sorry, that's not the point. I mean, I broke it, right? I added
Yeah,
some,
so it's broken, right?
yeah, but it's broken in a very specific way.
Correct.
But here you want to kind of treat it like a Fourier Lorentz tool.
The Lorentz symmetry?
Yeah.
Yeah, I mean,
So you're gonna write Lorentz invariant actions.
yes, I broke it in a very specific way, which allows me to write down EFTs that I know exactly how it's broken also in the EFT. I broke it in a very mild way. Let me make comments about this weird EFT. So the weirdest thing about it is this square root. There's some weird non-analyticity in this EFT, so I have to explain how I get around that because we're not used to seeing these weird EFTs. So So the way we get around that is that I still have to tell you here that I'm working around some large charge background. So I have to tell you how the charge comes in here. So we said the symmetry is still chi goes to chi plus one or chi plus alpha. So out of this, we can see how we set the charge here. The net current, you can just compute this. The net current is something like d pi d mu chi. And so the charge is d chi d zero chi dt. So in order to set some charge to be constant, what I do is I actually work around a vacuum, which is a constant times time for this Gaussian boson instead of around zero. So I'm not thinking of this Gaussian boson as originating around zero. The Web is not zero. Instead, I work in some weird background where it's linear in time. So this is some small fluctuation, and if I plug this ansatz back in and expand and work with the small fluctuations that of chi, then it's going to be completely analytic in chi hat. So this non-elasticity is not a problem. We just have to work around some weird background which sets the charge to be constant. Just for fun, so plugging this back in, we get Q is proportional to mu squared. Okay. So now let's try to get some mileage out of the CFT. So what can we actually learn about the CFT, assuming this CFT is correct? So let's do a computation. What I'm going to compute is something called delta min of Q, which I'm going to define as the minimal dimension of all operators where the operator has charge Q. So let me explain what this looks like. So here's all of my operators in the CFT. They all have some charge and some dimension. Here we have the identity operator, which is some neutral operator of dimension 0. And then we have other neutral operators.
You don't care what spin?
No, for now, no. We have some charge 1 operators that start here, some charge 2 operators, and so on. And this delta min of Q is, I imagine, some line that connects all of these minimum dimension operators. And this line gives me this delta min of Q. So large enough Q, I can think of this as some continuous function. You can add spin as well, and you can do some two-dimensional phase diagram, which is nice. But for this talk, I'm just going to focus on power charge. Okay, so how to compute this? I'm going to use the state operator correspondence. So I'm going to take my EFT and put it on the cylinder. And so instead of computing the dimension, what I need to compute is the ground state energy at a fixed charge. So this is by the state operator correspondence. This maps to delta min of Q on the backspace. So this computation is relatively easy. What I'm going to do is look at my EFT and try to look for a configuration or guess a configuration which minimizes the energy. This is again a guess, so this is another sort of logical leap where I guess that this configuration I gave you before, which is just some linear in time solution, that this solution is the ground state on the cylinder. There's some arguments for why this is true, but in general, again, this is some guess. So that's what happens when we plug this in. We already saw that this configuration has charge, which goes like mu squared. You can compute the energy momentum tensor for this EFT, and very schematically, it looks like d chi cubed to mu. So plugging in this configuration again, this gives me mu cubed. And so putting this together, I learned that the ground state energy goes like mu cubed, which is q to the power 3/2. So putting all this together, at large enough charge, what we expect is that this delta min of Q in a generic CFT, or whenever this boson boson exists, to behave like Q to the power 3/2 plus corrections at low orders in Q. So this is already a nice result. This is true, again, in many, many different CFTs, and it's been shown that even if you take Q to 1, this is still a pretty good approximation, even at relatively low Qs. But even beyond that, what this whole formalism allows you to do is not just take the leading term, but also compute systematically all of the corrections. So in 3D, you can systematically show that delta min q goes IQ to 3 halves plus specific square root of q correction and order 1 correction, and so on. And all of these terms, you can in principle compute them systematically. What you do is you go to the next orders in the effective field theory or compute quantum corrections, and that gives you all of these different types of corrections. The only thing you cannot compute are the coefficients here. The coefficients just come from the fact that you have an effective field theory which has its own Wilson coefficients that you don't know how to fix unless you have some more information from the UV that you started with. But this whole procedure does give you the form of the expansion in large charge. So this is the example of some computation you could do for any Shawnee coupled CFT just using this large charge expansion. Okay, any questions? Okay, good. So now I'm going to use this philosophy for the large charge expansion to try to answer a completely different question. So I'm going to try to bootstrap CFTs with moduli spaces. So let me start by explaining what a moduli space is. I'm going to take some simple Fourier theory with two real fields, phi 1 and phi 2. Just write down a potential, which is phi 1 squared, phi 2 squared. This is just a classical field theory for now. This theory has many different vacua. Basically, the potential vanishes wherever either phi 2 is 0, with phi 1 being any arbitrary number, or phi 1 is 0 and phi 2 is any arbitrary number. So I have a continuum of solutions to the vacuum equations. So this is what I call a moduli space. And instead of just having one vacuum or two vacuums, I just have a continuum of vacuum. These are very easy to construct classically, I just did. However, once you start including quantum corrections, these things are generically lifted. For example, in this example, once I include quantum corrections, a mass term is going to show up that looks like this. And this immediately gives an energy to all of these solutions except for the trivial one, except for phi 1 equals phi 2, 0. So this is the entire moduli space except for the origin.
You can tune that.
Sure. Classically, I can do anything I want.
Quantum mechanics.
I can tune it. There's other terms, it's going to be other terms that are going to fit the moduli space.
That's a non-trivial thing. The fact that there's a mass is why.
Sure. I gave one example of sure. I cannot think of an example that doesn't require an infinite amount of tunings and doesn't have supersymmetry. Yes. So the only way we really know how to preserve moduli spaces to all orders is with supersymmetry. So supersymmetry sometimes preserves moduli spaces. So I'm going to give examples. I'm going to give a very supersymmetric example and then a not very supersymmetric example. So a very supersymmetric example is n equals 4, including Mills theory. This has some gauge group, let's take it to be SUN, and has 6 scalars, xi, which are in the adjoint of G, and the potential, which looks like this, it's trace of xi, xj squared. So if we just think about this classically, we can look for the space of vacuum, which is just where this potential vanishes, and that vanishes whenever all of the xi's are diagonal, with whatever values on the diagonal. So ai1, ai. So if all of them are diagonal, then this vanishes and we have a very nice moduli space, which is very high dimensional. So if n is large, this is of order, whatever, something times n. So very, very large moduli space. And the magic of supersymmetry is that this thing is not corrected by quantum corrections, and the moduli space just remains exact to all orders. A less supersymmetric example, which is closer to what I want to talk about today, is the 3D n equals to XYZ model. So this consists of three chiral superfields X, Y, and Z. And the superpotential is just a product X times Y times Z. So if you're not used to supersymmetry, the way you read off the moduli space here is you solve something called the F-term equations, where you take the derivative of the superpotential with respect to every one of your fields and set it to 0. The solutions to these equations give you the moduli space, or the space of that field. So in this case, you have to take dw dx, which gives you y times z, and set it to 0, and then another equation gives you xz is 0, and another one gives you yz is 0. And the solution to these equations is that one of the three fields gets a vev and the other ones vanish. So either x is non-zero with y and z vanishing, or cross permutations. So again, this analysis is completely classical, but supersymmetry is magic, and it preserves the form of this superpotential and doesn't have one corrections, which will lift the moduli space. So this moduli space is actually there exactly to all orders. Okay, so now the question we want to ask today . I want to understand how a moduli space affects the CFT from first principles. So all of the discussions we just had are with Lagrangians. So given a Lagrangian, I can tell you if the theory has a moduli space or not. But I just given a CFT in a more abstract way in terms of dimensions and spins and OBE coefficients, it's not clear how to tell if the CFT has a moduli space or not. So one question is, given all of the CFT data, dimensions, spins, OBE coefficients, can you tell me if there's a moduli space or not? And the other direction is just the other direction. Let's say I give you a CFT with a moduli space. Can you write down some constraints on the CFT data? So even though once you have a Lagrangian, understanding what a moduli space is it's very easy, it turns out that these questions are extremely difficult. They've been around for a while. These are very fundamental questions that have been around for a long time, and there's very little answers to these questions. What we're going to do is we're going to solve these questions under a small assumption, which is that I'm allowed to use large charge. So assuming that there's also some U1 symmetry that's broken on the moduli space. So a U1 symmetry that spontaneously broken on the moduli space. We're going to make progress and actually try and manage to find some very nice constraint on CFT data using the vectors of the moduli space. So we're going to solve these questions just assuming there's an additional U1.
You assume just U1 is broken everywhere or only at specific points on the moduli space? Or?
No, everywhere. If usually what happens is that maybe it's preserved at the origin, but it's going to be broken generically. It's hard for it to be broken at one point and not everywhere else. Okay, so before solving this question, let's ask what's already known. So with enough supersymmetry, we can basically answer this question. Most examples of CFTs with moduli spaces have at least 4 supercharges. So if you just ask some random person on the street, he would give you an example, which is either 4D n equals 1 supersymmetric or higher, or 3D n equals 2 supersymmetric or higher. So these two have 4 supercharges. And if you assume this, then we basically know the answer. There's a conjecture which tells you that the moduli space, these theories, is isomorphic to something called a chiral ring. This conjecture was proven for Lagrangian theories, but it's conjectured to be true in general. without explaining what a chiral ring is, I don't want to go into details. All of this conjecture means is that the only operators that can get a web and take you in some direction in the modular space are BPS operators. And not only is phi itself BPS, but phi to the n is BPS as well. So only very special protected operators can take you in directions on the modular space. And this immediately gives you everything you want to know. So we immediately learn, one, that there's a U1 symmetry that's spontaneously broken on the modular space. The reason is that all of these theories, if they're CFTs, they have something called an R symmetry. And these BPS operators are always charged on B4 symmetry. So all of these examples immediately fall under the case where there is some U1 symmetry that's broken. So this already looks like a good assumption. And the second comment is that the fact that these things are BPS gives you a constraint on CFT data. It tells you that there exists a tower of operators such that the dimension of phi to the n is n times the dimension of phi. This is just because they're protected, so supersymmetry is magic, and it gives you this nice constraint. So we already have a guess for what it means for a CFT to have a moduli space. It's just this statement. So tower of operators, where the dimension is linear in whatever n is, delta phi to the n is n times delta phi. And if you asked, again, some random person who works on supersymmetry, this is probably the first thing they would tell you. But there's a problem with the statement because we are very heavily using this R symmetry, or the fact that these operators are BPS. So the fact that there's a lot of supersymmetry, there's 4 supercharges, is playing a very strong role in all of this discussion. So in order to think about this from a more abstract bootstrap perspective, to think about moduli spaces without having to use supersymmetry, we need to think if there's examples of moduli spaces with less supercharges and with no R symmetry and with no protected operators.
So for example, with more superchargers, that also do.
But then this falls under this.
No,
What do you mean? Give me an example.
5 and 6 dimensions, they're a theory
Yes,
of 8
you're right.
superchargers that do not have a R that have an R symmetry, but there's
In
no,
5, I agree.
there's no,
So
there's no chiral ring. Also in 6.
I'm not aware of the 600 example. What is it? What is it?
61. Almost all 61 zeros.
No, this statement is still true in 16.
No, absolutely not. It's true roughly for half the operators. There's a Higgs branch.
Yes.
But there's also
Oh, there's a
tensor
tensor branch. Oh, you're doing one. Okay, you're right. These are going to be the same types of examples I'm going to talk about. Yes, so 5D1,0 and 6D tensor branches don't have this, and I don't have answers for those yet, but I do have the. Okay, sorry.
But maybe we'll come back to it. But even in this, the boring case, quote unquote, there's an interesting question, which is so we know that there's this magic protected subset of operators which controls the moduli space. But it's not true that they're the only ones that get that. Everybody gets a that, including the long ones.
Everybody, many operators get a web, yes.
Almost all, generically, almost all operators, unless they're restricted by symmetry, get
Yes.
that. Yeah, there's still an interesting question of what is there any universal thing you can say about the best of the sort of non-BPS?
Yes, we don't have an answer to that. There's a bootstrap equation you can write down. And I mean, we wrote down the equation, you can do it in perturbation theory, but we don't have a nice universal answer that you can just say, oh, this is the result you get. So with one type of this answer we can give in general, this more general question is still an open problem. I can talk about what the bootstrap equation is and what to try to do with it.
Yeah, you could try to compute the 1-point function of Cauchy.
Yeah, that you can do, for example, if you have another perturbative parameter, you can do that from first principles. But yes, but you need some other perturbative. There's no first principles derivation I can give you. Okay, so we need examples of moduli spaces with no BPS operators or no U1R symmetry. So these exist, and the example I'm going to focus on is 3D n equals 1 supersymmetry. So let me explain what this is. So 3D n equals 1 supersymmetry has 2 supercharges. This is a very low amount of supersymmetry, and as a result, these theories are not very well studied. The reason is that on one hand, you have supersymmetry, so it's not really predicted in nature. And on the other hand, it's not enough supersymmetry to help you compute things, so it's not even a good toy model. So for example, these things have no continuous R symmetry, no U1 R symmetry. They have no BPS operators, no non-renormalization theorems, all of the usual things that you like to use with supersymmetry are just absent in these models. However, it turns out that there's still enough power here to argue for exact moduli spaces. So still, you have exact moduli spaces. So let me argue for these things. Let me show you how they show up, even though you don't have a good R symmetry, a good continuous R symmetry. So a simple Lagrangian for a 3D=1 theory, just like any other supersymmetric theory, it has something called a Kähler potential plus superpotential. I'm thinking of what?
Oh, you want to split these artificially?
No, it's not artificial. This includes derivatives. That doesn't. It's like a kinetic term and a potential term. No, we do this all the time. Yeah. So, given
We
some,
usually don't at 3D=1, that's what I'm saying.
I'm still going to do that because it is going to be useful. So Thomas's problem is that, unlike in higher theories, in higher supersymmetric theories, where I have a Kähler potential which is integrated over all of superspace and a superpotential which is integrated over half of superspace, that's just not possible with 3D=1 because I cannot integrate just one Grassmann variable. This is weird. So there's no real distinction between a Kähler and a superpotential in 3D=1, except for the fact that I'm going to include derivatives here, but not here. So it's like a kinetic term and potential term. So the simplest example, if I just have some simple matter field, is to take K to be some kinetic term and superpotential is phi to be n, some potential. Again, if you're not used to supersymmetry, if you have a superpotential, the way you read off the usual potential, so take dw d phi, where this is any one of the fields, and take this sum of all the fields. So now, even though we don't have a continuous R symmetry, it turns out there's still a discrete R symmetry in these theories in some specific cases. So there's a discrete R symmetry. So let me show how this happens. With a Lagrangian, the way you usually read off an R symmetry is that it acts on the superspace variables. So this has some weight on the R symmetry, and then the superpotential just has to cancel that weight. So if you had 4D=1, what you do is give this some charge of their U1 symmetry, and W would just have to have the opposite charge. You can't do that here. Instead, what you can do is give this a discrete R symmetry by taking d2 theta to minus d2 theta under some C2 symmetry that you require. This is like a time reversal transformation. You can think of theta as some Grassmann, some fermion, and so d2 theta goes to minus d2 theta for time reversal, 3 dimensions.
I think it's very important that it's not an R symmetry. That it has to be anti-unit.
I want to call it an R symmetry. I know. I want to call it an R symmetry. You want to call it time reversal? Then just
Not yet. We don't not unitary.
for me, an R symmetry just acts on the superspace variables. This is what I mean by
R symmetry is also an R symmetry. That's very confusing.
Let's call it time reversals. I'm going to keep saying R symmetry and then you just correct me when I do that. But yes, time reversal symmetry. So for this to be a symmetry, of course, we also need this superpotential to go to minus itself. So assuming you have this symmetry, it prevents specific terms from showing up in the superpotential. Any term that breaks the symmetry is now prohibited. And this simple Z2 symmetry is already enough to provide exact moduli spaces in some examples. So let me give the simplest example. The example is the 3D n=1 ABC model, which consists of 3 fields, superfields A, B, C, and a superpotential which is A and B times C. So this looks similar to what I call the XYZ model, which was 3D n=2. The only difference is that these are real fields, and so there's no U1 symmetry, while these were complex. If you take the ABC model and call these complex fields, it's just exactly the same as XYZ. So let's study this model. So let's start just classically. Classically, there's a moduli space. I solve the F-term equations again. So dW dA is 0 tells me that B times C is 0, and then I have another equation, which is this, and another equation, which is this. And again, just solving these equations tells me that a vacuum is either with A getting a vec and B and C vanishing, or permutations of this. So at least classically, there's a moduli space. And the important question is what happens when I add quantum corrections? So let's try to write down the most general quantum correction that can show up to this theory. So I'm computing now the effective superpotential, including all the quantum corrections. A term here will be some generic polynomial in A, B, and C. But of course, it has to preserve the symmetries of the original model, and that's when constraining what type of terms can show up. So one symmetry is just permutation symmetry of A, B, and C, so this has to be symmetric in A, B, and C. But more importantly, we have a time reversal symmetry, which is preserved in this model, which takes d2 theta to minus d2 theta, and also takes the field A to minus A. Right, so W is odd on this transformation, and so this is preserved.
Doesn't do anything to B and C.
For now, no. So for this symmetry to be preserved, this polynomial P has to be odd in A. So the only possible form is A times some other polynomial, call it P prime, which is a function of A squared, B, and C. But of course, choosing A here was completely arbitrary, and I could have instead chosen, instead of this, I could have chosen B to minus B. And this is still a time reversal symmetry under my problem, and my effective superpotential should still preserve the symmetry. So this polynomial should also be odd under B. And exactly the same argument works for C. So the only possible term in my effective superpotential is something that has A, B, C outside, and then some polynomial of A squared, B squared, and C squared. Now we can again look for a moduli space. We can take this most general form for the superpotential, solve the F-term equations, and you can show that these solutions are still there. Basically, because of this term outside, if I set two of the fields to 0, that's enough to make sure that I'm in a vacuum.
You just stick to renormalizable terms?
Sorry, are you asking me? No, this is all possible terms that can show up in the effective superpotential.
Why is that necessary? I mean, the model is renormalizable, so why can't we just look at the renormalizable?
No, that's not how you get a modular space, right? I mean, if
This model is renormalizable. You were thinking of talking about the effective action on the moduli space.
sure, yeah.
That's not. Why is that?
You're saying it's enough to look at the relevant informations, and if they don't hit the modular space, then there's a modular space in the CFT? I think
No,
that's right.
it doesn't need to be relevant. It could also be marginal, but you don't need.
Oh, sure, but
You don't need to. Confused.
if I want the modular space to be there, like, okay, I'm telling you that
No, you're.
V can be arbitrarily large, right?
You want to look at the moduli space effective action.
Yes, so I want V to be arbitrarily large.
Around this vacuum. Okay. So then you want to talk about non-local terms and all these kind of things. In fact, it's not general not a polar.
Why not? No, okay, if I know they're large enough distance, I mean, there's not gonna be some strongly coupled theory far enough away in the modular space. There shouldn't be some weird thing.
No, it could be decay. It could be something that's decay. Like a power.
I said polynomial, didn't I? Okay, yes, right, it could decay, yes. Not polynomial, some rational function of these things.
Right.
No, sorry, no. At large enough distances, it should be some nice analytic function of these fields, because I know it's weakly coupled, like it should be some massive theory when I go far enough away on the modular space.
Wow, famous runaway example.
But those are strongly coupled theories, so when I don't have any gauge fields, those things should not happen. I agree once I have gauge fields with some weird things I need to take into account. But if it's just some Western model, this should be the form with the polynomial, like maybe it's C.
What's the model in 3D? It's just a strongly coupled case.
No, I'm saying that at large distances on the modular space, everything is weakly coupled. There's no strongly coupled sector.
That's also true in the gauge theory example to get the.
No, I still get some confining gauge theory is strongly coupled and things can happen.
You have completely Higgs example. The basic ADS potential is completely Higgs. Completely weakly coupled. There's no strong gauge dynamics. That's the whole point.
When it's completely Higgs, there's still a runaway?
Yeah. It's the one of that's the canonical example. the first and canonical example, when it's completely Higgs, then there's the 1 over meson runaway. It's true that the potential becomes small as you go to infinity on modular space, but it doesn't need to become analytic.
Yes. I understand. Can I say perturbative and then are you okay?
Sure.
Which is, there are examples of non-perturbative, but this is.
For considering realizable potential.
Yes, that's right, that's right.
We'll give you the same answer.
That's right. That's right.
Yeah.
There are examples of non-perturbativity, these things are lifted, just like in the
Right.
runaway example.
Even with Wesleyan models.
No, I don't know of examples. With Wesleyan models, I expect this to be the answer. Okay. So the bottom line is that at least perturbatively, what we found are these 3 equals 1 theories with no U1R symmetry, no BPS operators, but moduli spaces are still there.
Sorry, can I actually ask, do you need PR symmetry in this case? I mean, doesn't the permutation symmetry already?
No. It's not enough. So the permutation symmetry doesn't rule out a mass term, right? So I can write down. Okay. And this immediately lifts the moduli space. So yeah, it really is the R symmetry. Sorry?
It was like A cube plus B cube plus C cube.
There's infinitely many terms that lift the moduli space of 2. Okay, so now we have a new question. So in these examples, what do we expect for this delta min of Q? Sorry, I went too fast. So in these examples, what do we expect to be able to say about these towers of operators we had before? So with enough supersymmetry, we said, oh, okay, there's a moduli space, and there's this tower of operators for any n. But now with no R symmetry, this statement doesn't even make sense. It's not clear what we mean by taking phi to the n if phi itself is not some projected operator. So instead of using this statement, I'm going to say, oh, okay, with enough supersymmetry, the correct statement is that this delta min of Q, instead of being Q to the 3/2 or Q to whatever for a generic CFT, it's actually linear in Q, some coefficient alpha times Q. So this, of course, reduces to this, and in the case you have BPS operators, but this is a more general statement that you can talk about even if you don't have an R symmetry. So our new guess is that a CFT with a moduli space with some U1 symmetry obeys this equation and not the previous generic example we had before. So this is a natural guess, both because our previous examples are very supersymmetric examples with BPS operators obeys this, and also free theories. So a free scalar, which also has a moduli space, also obeys this type of equation, right? So if the free scalar is phi, phi to the n has charge n and has dimension n times t minus 2 over 2. And these tell you that delta min is again linear in Q up to some coefficient.
General here, there's no notion of a charge, right?
Sorry, Ken?
In general here,
I'm always assuming there's a U1 symmetry that's broken. You're right, this doesn't fall under my examples, but yeah, there's other examples where there's an example. This was just a simple example of how you get a moduli space in 3 equals 1 theories. Now imagine an example like this with also a U1 symmetry, and then this applies. In the motional case, again, we have this bootstrap equation, but I'm not going to get some nice answer like, like this, or what it means to have a moduli space. Okay, let's try to prove this. Or let's try to check if this is true. So what I'm going to do is use the methods we learned from the Welsh charge expansion. So what we need to do is figure out, once we go on the moduli space, what are the low energy degrees of freedom, and then what are the symmetries that constrain them, and then write down the most general effective field theory that you can write down. So let's assume we have some CFT. I'm not assuming supersymmetry now, with a moduli space, and some U1 symmetry that's spontaneously broken on the moduli space. And I'm going to ask, what is the effective field theory at some generic point on this moduli space? the massless degrees of freedom are again a Goldstone boson because assuming this U1 is broken, a null Goldstone boson. And in addition, now I have something called a dilaton. Because I'm assuming there's a moduli space, I'm assuming some spontaneous breaking conformal symmetry. This dilaton is what takes me to large enough distances on the moduli space. So this is different from the effective field theory we had previously, where we just assumed we only have this Goldstone boson. And this is going to give us some different terms in effective action that will lead us to this behavior instead of this behavior. And I'm going to show you explicitly. So these are the massless degrees of freedom. We also have symmetries that we expect the EFT to preserve. One is the U1 that we started with, which is now non-linearly realized. And we also have this whale symmetry, just like before. And now once more, we write down all of the possible terms in the EFT, order by order and derivatives. So here's my EFT. It's going to be a two derivative term, four derivative terms, and so on. Now, two derivatives, these symmetries fix everything up to one number. So we have a kinetic term for the dilaton, which is the conformally coupled scalar, and a kinetic term for the Goldstone boson, which is also coupled to the dilaton, and this is some Wilson coefficient that we don't know the number. It's some number that you have to have some UV information with this. And these are all of the possible terms of two derivatives. And in general, now you can go on to four derivatives and six derivatives, just write all of the possible terms. The next step to find this delta min is to put this theory on the cylinder. So work on 2 times R and look for a ground state. The guess is this. So the Goldstone boson has exactly the same form it had before, and the dilaton just has some constant by V. Again, there's good reasons to use this guess, but for now, for us, it's just going to be a guess. So let's plug this in and see what we get. So first, let's fix the charge. The usual Netlist theorem tells you that the charge is phi times dt chi. Sorry, phi squared dt chi, which in this case gives you v squared times mu. And if you compute the energy momentum tensor, you're going to see that it's proportional to v squared. Putting these two together, what you find is that the energy is proportional to the charge, which is exactly as you want to see. So at least at the two derivative order, at least at order two derivatives, we get exactly the linear relation we want. Now, of course, we have to go to higher orders and derivatives and see if they contribute. What are the possible corrections that can show up? So one correction is just higher orders and derivatives. So you go to the four derivative terms, and in principle, these can contribute as well. So from dimensional analysis, if this is a four derivative term, let's say in 3 dimensions, so I have some term which is d3x, four derivatives, and the only term that can show up to fix the dimensions is 1 over the dilaton squared. And if I plug in our ansatz here, this scales like 1 over v squared, which in terms of the charge gives me 1 over q. So naively, I expect that at least for four derivatives, I'm going to get a 1 over q term. And if I keep going to high derivatives, I'm going to get 1 over q cubed and more corrections. A second type of correction is quantum corrections. Spanning around some saddle point, you need to take into account these quantum corrections. Basically what happens is that your 1 over q, your charge, becomes the h bar of the theory. And so a loop expansion in h bar just becomes an expansion 1 over q. So if the leading term is q, the next term is going to be q to 0. Then it's going to be 1 over q term, 1 over q squared, and so on. So if I take all of the corrections in the EFT into account, then I don't get this result that we expected. And instead, just assuming a moduli space plus a U1 symmetry gives me the following behavior. Delta min of q is some expansion. It's q plus here 0, 1 over q, and so on with coefficients that for now I can't fix. So this smells like the type of answer we wanted, just assuming there's a Moduli space to have some universal constraint on CFT data. The last step is to really see what I can say about these coefficients. So up to now, the only examples I've given you were examples with 3D n equals 2, where there's a lot of supersymmetry, and where this statement is exact. And Suzy magic just makes all of these cancel. So to really make sure that this is the correct statement, I need some example where I can compute all of these corrections and show that they're non-zero. So we sat down, and there's a few separate examples. You can just really sit down and in perturbation theory compute what these corrections are, and they really are non-zero for theories with 3 n equals 1. So the correct answer, if you just assume there's a Moduli space, is not that delta min of Q is just linear in Q, but that asymptotically it's linear, but you actually have corrections that you have to take into account.
Which examples did you compare?
Right. So one example is 3D n equals 1 SQED. So this is QED. So with 3D n equals 1, you have a gauge field and a gauge genome, and then you have matter fields phi I, psi I, with NF flavors. This classically has a Moduli space. The superpotential is just 0, just classically. So you have a Moduli space parameterized by these phi I, and it's just a CPNF minus 1 model, right? There's a symmetry written pattern, which is SU and F, broken into SU and F. So this is just CPNF. And now you want to do quantum corrections. It turns out that the Z2, that the time reversal symmetry is enough to keep W to 0 to all orders in perturbation theory. And so this Moduli space is just exact to all orders. And now you can compute the corrections.
So you don't mean CPNF, you mean the cone over that.
That's right, plus a dilaton. Yeah, times dilaton. That's, yeah, sorry. Right, so now what we did was this term is easy to compute. And this term, the only contribution comes from quantum corrections. It's basically the Casimir energy. Right? And so it's just a matter of computing the Casimir energy on this weird EFT, and it's not 0. And the paper has some other examples, but this is the easiest one. Okay, so this is the result we're looking for. So some universal constraint on CFT data just by assuming there's a Moduli space. I didn't even assume supersymmetry to get this result. It's just assuming there's a Moduli space.
Just so I make sure like the d chi to the 3 halves is inconsistent with phi, or why is it not showing up there?
Right, so because this example has a Moduli space, I am assuming some locality, which means that I cannot have fractional derivatives. So it is Weyl invariant, but it's not local. The idea is that now, because there's a Moduli space in the theory, I should be able to expand both phi and pi around any vacuum, any, whatever, any number, and it should give me a good local theory.
Right.
And d chi to the 3 halves is just non-analytic. So the previous example, I could only make sense of it around UT. But now I should also be able to expand it around some constant, and that rules out this term. Okay, so I'm gonna make some short comments about what we can still say about the coefficients in front of these terms. So in general, these coefficients are some Wilson coefficients, and you have to go term by theory and compute them. But we're trying to look at constraints or some inequalities that these coefficients have to obey. I'm going to give one example, which is this beta coefficient. So a couple of years ago, there was a conjecture for what it means for what the weak gravity conjecture means for CFTs if you apply the ABS CFT correspondence. So let me explain what all of these words mean. So the weak gravity conjecture is an idea that was born out of black hole physics, which says that for any theory, any effective field theory, some QFT, that can be consistently coupled to gravity. So some UV theory of gravity is its origin. Can be coupled to gravity. Such a theory there has to exist a particle whose mass is smaller than its charge under some U1 symmetry. In whatever units. So it's clear why this is called the weak gravity conjecture. This is some charge under a U1 gauge symmetry, while the mass is a charge under gravity. So gravity is the weakest force in the sense that there's always a particle which is the weakest force. And this statement has had many different iterations. It is still a conjecture, there's no proof. And it's one of the cornerstones of what's now called the swampland program, which tries to find many other constraints on EFTs that can be consistently coupled to gravity. And all of these things usually remain conjectures and are very difficult to prove. But one idea is if you can now take this statement, put it on ADS, and ask what it means for the CFT side. And since we understand CFTs much better than we understand theories of gravity, you can now try to prove from the CFT side whether this thing is true or not, at least on ADS. So one proposal for what the weak gravity conjecture means on ADS is what was called the CFT convexity conjecture. And the proposal was that if the weak gravity conjecture is true on ADS, then on the CFT side, this delta min of Q that we talked about should be a I forget what it's called. Let's call it convex, super additive function. Basically, delta min of 2Q has to be larger than 2 delta min of Q. So this statement is immediately wrong. You can write counterexamples. And so instead you write a small change. And what you say is that it's super additive in units of some basic charge. So N1Q0 plus N2Q0 has to be larger than N1Q0 plus N2. So it's still super additive, but only in units of this Q0, where Q0 should be some number of order 1. Okay, so this statement is not obviously false. It takes longer to find a counterexample, but again, this statement was proven wrong. And the next statement is to just say, okay, I don't tell you, and I don't give you any constraints on Q0. I'm just telling you that there's some Q0 for which this is true. This seems almost trivial. And the reason is a large charge expansion. So I told you today that a large charge, so if Q is large enough, then we've only found 2 behaviors today. One is that delta min goes like Q to the power D over 2 with D of space-time dimension. And this immediately obeys this equation. This is some convex function. And the other behavior is that it's linear in Q. As in exactly alpha times Q, and this is either in the free case or when you have BPS operators. So in all of the previously known examples, this was immediately true at large enough Q, and so this statement without the assumption that Q is a 4 to 1 is practically meaningless, or it's equivalent to this statement. But what we've seen today is that there's actually a new type of behavior that wasn't known before, which is this type of behavior, where only asymptotically we get some linear behavior in Q plus small corrections. Since the asymptotic behavior obeys this inequality exactly, it saturates the inequality with an equal sign, that means that for this to be true, there has to be some constraint on the coefficient of the next term. And it turns out that for this to be true, the constraint is that this beta here, the constant term, has to be negative or non-positive. So another way of realizing the weak gravity conjecture and the CFTs is to say that this beta has to be non-positive. We sat down and tried to prove that indeed this is non-positive, but this seems like a reasonable thing to prove because this is just a Casimir energy, like I mentioned. This is something that you can compute in general, and we just expect Casimir energies in general to be negative. We could not prove this in general, but in every single example we did, this is indeed negative. So
can you relate this back to the Wilson coefficients in your EFT expansion?
yes, you can. I tried using these less matrix
Can you
constraints.
use versatility bounds and those are the dimension of the operators too low about these the next operator that's relevant.
I don't think that's a problem.
But it's about subtraction terms, right?
I think you just need to know basically the 4 derivative terms.
Yeah.
But it's some combination that I haven't found positivity bound for. I agree that's very natural to try to prove it that way, but we couldn't.
Sorry, why are you talking about the 4 derivative term? I mean, that's subleading to your beta.
Oh, sorry. Sorry. I was confusing with this coefficient. This is just a quantum correction. It's really just computed quantum correction. You can prove that it's negative for some specific families of theories, but we couldn't do it in general. This is not, you cannot use the positivity bounds, or the usual ones you use. Yeah, so unfortunately, we can't prove it in general. For all of the examples we've looked at so far, it is negative, and we're still trying to show that it's true in general.
So even in some cases, you can use unitarity, basically perturbing unitarity to even balance some quantum corrections, I guess.
Is it something that's not trivial, as in it's not just something that has to be done?
Yeah, it's not trivial.
Okay.
Adar Sharon had some papers, I think.
Okay, maybe we can talk about it.
Yeah.
Yes, I think it's still open as what Thomas said. So 5D n equals 1 theories also have moduli that are not charged under an R symmetry, and 6D theories also have moduli that are not charged under an R symmetry. The problem is I don't know how to do computation in these theories. So here I had epsilon expansion for 3D n equals 1, and I had large n. I can just do computations and just find whatever the coefficients are for these.
You know what? You know the moduli space of vector theory, which should be enough to compute Q to the 0. It's just a Casimir.
In 5 dimensions, it's different. In 5 dimensions, the leading term is not the Casimir. So this is only true in 3D.
Yeah, it's going to be some curvature.
Yes, in 4D, the situation is already different.
No, but the good thing about those examples is that despite the fact that they don't have these protected operators, they have 8 supercharges. So the low order and derivative terms are very constrained by supersymmetry.
Even on the in 5D, even on the Coulomb branch? The Higgs branch, I agree.
No, it's much better on the Coulomb branch. The Coulomb branch is much more protected than the Higgs branch.
Yeah, I think it's just a free theory, at least in the examples I can think,
but it has a very restricted. So in 5D, the pre-potential can be at most cubic. And even when you start, that's pretty much it. In 6D, it's even worse, where
I don't know about the 6D. What was it worse?
No, well, it's better. It's even better. It's even more.
It's just a free the rock
No, it's a tensor multiplet. Whose kinetic term is completely trivial like this. Then there's a 4 derivative term, which a priori looks unfixed, but it's actually fixed by anomalies. Because it's the superpartner of the Green-Schwarz term. So it's exactly.
The derivative term is completely it's trivial.
The derivative term is trivial. It's completely rigid.
Okay, it's just a free. Oh, okay, it's not gone. It's just. But there is a 4 derivative term.
Yeah. So there's no metric. It's just flat. And there is a 4 derivative term, which is non-trivial in terms of the scalars and the fermions, but it's the superpartner of the Green-Schwarz term. So.
Oh, I understand. Okay.
So at least in many examples, you can also determine. So I wouldn't be surprised if up to 4 derivative orders.
This was with 1,0 and 60. With 2,0, I knew this.
1,0. So this
is okay.
With Clay and with Ken.
Okay.
Long ago on the 8th theorem and so forth. But the main point of the paper was to fix the 4 derivative terms. Good.
So in 60, what you'd have is this, and this will be from 4 derivatives. So you're saying this is computable?
Yeah.
Okay. Even on the tensor branch. I didn't know that.
Especially on the tensor branch. In fact, we never got to it. We're able to compute it on the Higgs branch. On the Higgs branch is not fixed.
Oh, I'm remembering now. No, in both of these examples, there's no U1 symmetries. In 5D,
there's not one symmetry.
There's no sorry, what?
There's no U1 symmetry.
Okay.
It's still an interesting question.
No, but then I don't know how you ask this question without a symmetry.
But
question. So what you want to say is, okay, so let's forget about the U1. Now you have a natural conjecture, what it means to have a moduli space without a U1 symmetry. You still have that in whatever sense. You have a tower of operators that are almost integer space.
You just have the delta.
Yes, but this is a meaningless statement because here's a spectrum for a CFT. You can always find operators which are almost integer space that become integer space as they go asymptotic. Right? It doesn't even have to be integer. This is not a, just some constant spacing. I don't know what the correct statement is without a U1 because they can't even ask the question. Any CFT is going to have states which are approximately constantly spaced as you go to high dimensions, just because it's some chaotic thing. So part of the reason I need the U1 is to even make sense of what it means to have a tower of states. Once I have a charge, then I can set these states apart and say these are special tower states.
Yeah, you're not gonna get that. Nobody knows what that is.
Yes, so how do you never find n equals 1?
Well, it's the same. Good point.
There's no examples where you also have some global symmetry?
No.
You can prove that this cannot happen?
No, it's obvious, and because the Coulomb branch is it's just like your 3D n equals 1 example. The Coulomb branch is parameterized by real field. And there's no R
Yeah.
symmetry that adds something.
What about 1, 0 and 60?
Same.
Again,
Tensor branch is a real scalar.
no, the fact it's a real scalar doesn't mean you can't have, so let's say I have some, more than one direction, I can have some global symmetry interchanging.
No, because these the scalars are the super partners of the tensor multiples.
Yes,
and
so the problem is that there are superpolars of gauge fields and
They're
yes,
not,
and
they're
then,
no continuous symmetries.
Yes.
And
right, so I don't know how to do this for either, or for 5 and 60. I don't know what the statement is to be told for. You can do, I mean, you can do that with just a dilettante, just like you said. There's some technical difficulties, but basically you can write down this, but I think it's meaningless. I don't see what it means.
It's not that you just have a dilettante, right? You have a dilettante plus its super partner.
Sure, I'm saying, assuming you just have a dilettante, you can reproduce this equation, whatever it means, but without Q, I mean, what delta of n is n plus corrections. You can write this down, but I think it's meaningless. What is this specific tower state? Like, how do you look for it in a safety spectrum?
We should see if there are other questions. All right, let's think about our Renaissance.